So actually, I wanna, okay, let's see the, okay, try the full screen. Okay, perfect. We see your cursor, perfect. So I wanna, particularly thank Malte because like Ben Safdie was supposed to give the talk and he had a last minute family problem. So really tonight. So Malte was, was giving this talk on a very, very short notice. So thanks a lot, Malte. And he's from Princeton, and he's going to talk about dark matter from Axion Strings that also kind of motivate some of the most interesting search that we listen to in these days. So please take the stage, Malte.
Yeah, hello everyone. So yeah, given that I'm a substitute for Ben on relatively short notice, just as a little disclaimer, the slides you're about to see are a mix of slides that I just had lying around, as well as slides that Ben prepared for this talk. So it's all a little bit of a patchwork, a little bit improvised, but we'll see how it goes. So the title that Ben chose was the QCD Axion Mass, and that's also pretty much exactly what I'm going to talk about. This talk will be mostly about the QCD Axion Mass and that you can predict it in certain circumstances and how you can do it and what we find, etc. So let's start with just the general introduction slide for Axions, even though I don't really want to say much. You all know that the Axion is one of the best motivated, arguably, Dogmata candidates, can also explain the absence of the neutron electric dipole moment. It has a certain mass that is relatively small, some sub-eV typically. And in the early universe, it's typically described by some complex scalar that follows a U1 symmetry that is spontaneously broken at some high scale Fa, where the breaking scale is also directly related to the axion mass. And that's pretty much all you need to know about the axions. Now, the axiom I'm going to focus on is the standard QCD Axion. So if you go to the typical exclusion plot that everyone shows, is where you have the mass versus the coupling of the axion to photons. The QCD Axion lives somewhere on this golden line down here. Now, regarding experimental efforts, there are plenty of experiments that are trying to access the line of the QCD Axion. And the problem that most of those experiments face is that in order to have some measurable effect, you rely on a resonance. You basically have to hit the right resonance. And that implies that as an experiment, you have to test every single mass point individually. And that, of course, is incredibly cumbersome, incredibly slow. And that's just what it is. So as an experimentalist, it would be really great if one could have a prediction for the axion mass where you can basically focus on first and start looking there. So the question is, can we predict the axion mass? And the clear answer is it depends. And the reason it depends is because there are several different scenarios that one consider, mostly two different ones, which is the post and the pre-inflationist scenario. Now, those two scenarios differ in a way where it depends on whether you break the Pq symmetry before or after inflation. And those two scenarios actually turn out to be phenomenologically very different. Now, what it means to break the Pq symmetry is basically you just, at high temperatures above the breaking scale, you just have your normal 5^4 potential, and then at some point you start seeing, the central broken potential with a bump in the middle. Now, the way you parameterize that, just to bring everyone on the same page, that you have a complex scalar field, so you have two degrees of freedom. The angular one is what we then call the axion, and then you have the radial mode, which is the radial component of the field. Now, if you break the Pq symmetry, what it means for the axion field the moment it's broken is you can see it's completely symmetric, completely degenerate. So if you just make a plot of the axion field, you see that it takes on every values between -pi and pi without preference for any particular value at all. So this is, if you look at the axion field, that's basically how the field looks like once you break the Pq symmetry. Now, if that happens before inflation, what inflation basically does, it picks one of those particular points in your field and it basically just inflates it. And all of your observable universe just has one randomly chosen value, basically, which is the misalignment angle, θ0. Now, if you, in the other case where you break the Pq symmetry after inflation, well, inflation has already happened, so you don't have this zoom in effect anymore. So what you already see here with all these Hubble size different Hubble size patches, that's basically what you get. And the global universe has all these different patches. And just from this simple cartoon, you can already see how different those two scenarios are. Now, in terms of predicting the Axion mass, it is, basically what you want to do is you want to count the degrees of freedom in your theory. So in the case where you break the Pq Symmetry for inflation, you have your breaking scale of A that you introduce, but then you also have this one randomly chosen angle θ0. So if you want to compute the relic density in your case, you actually depend on both of those different parameters. Unfortunately, we only have one measured value, so you can't simultaneously solve for both of them. So it's not really possible to predict the Axion mass in that case. If you, however, break the Pq symmetry after inflation, well, then you don't have this one randomly chosen value anymore. Now you basically just depend on the statistical mean of all of those different values. And that is something you can compute analytically. So in that case, you effectively have only one free parameter of A, one measured value. So in that case, you can actually predict the Axion mass. So for the rest of this talk, I'll basically just focus on the post-inflation scenario where the Pq symmetry is broken after inflation. Now, in order to actually compute the relic density, it is a little bit more complicated because you do actually need to understand the entire cosmological evolution of the Axion field in the early universe, because you can see from this image over here, the field state is rather complicated. So you need to do some numerical simulations in order to understand these properly. Now, just as a little summary about like what different stages the Axion field actually goes through throughout, starting at the beginning all the way to today. And there you notice that I just recycled some slides from a previous talk. So the different stages that it goes through is, of course, first thing is inflation, because we are working in a state where the inflation happens first, and then you break the Pq symmetry. And then at temperatures much smaller than that, at around a temperature of about a GeV, you go through the QCD phase transition. What happens there is basically you have this potential here, and then it starts tilting. In that case, you break the symmetry of the potential, and the axion actually becomes massive. Then at later times at redshifts of around 3000, you then hit the meta radiation equality. And at that point, your axion fields then also starts a gravitational collapse, and you typically see something like the formation of axion mini halos. Now, axion mini halos are like very interesting phenomenologically. There's a lot of interesting stuff you can do with them. Unfortunately, I don't really have time to talk about them. But my main point I really want to do here is that in order to understand and quantify all these different stages, you will have to run numerical simulations in order to understand the different stages. Something that I, together with Ben Safdie and Josh Foster and a couple other people, have been doing over the last couple of years. So the stage I want to focus on is the time between the Pq phase transition and the QCD phase transition. The reason I want to focus on that particular time is because the evolution of the axial field there is what ultimately sets the Axion mass. And for reasons I will explain on the next slide. So the reason this stage is so important is because during the Pq phase transition and the QCD phase transition, something called Axion Strings exist. What are Axion Strings? Axion Strings are topological defects where the axion field is essentially stuck on the hilltop over here. These Axion strings are so important. Well, so first of all, they're called strings because in 3 dimensions, they actually are forming closed loops. One is shown down here. The reason Axion strings are so important because, as you can see, they're sitting on this hilltop. So there's a lot of potential energy available. And while they evolve and do a lot of different dynamics, some of this energy is being radiated away. And part of it is basically ends up in the angular components or in axions. So ultimately what Axion strings do over time is they radiate axions. and they are, as it turns out, the main producer of axions. So if you want to understand what the Dogmata, the axion mass is, you need to understand the evolution of those axion strings, because they are ultimately what sets the axion number density, which is the relevant quantity. Now, axion strings, they are if you have a just normal domain over number 1, etc., they're not long-lived. They are created the moment you run through the Pq phase transition, so you start actually having this hilltop, and they are getting destroyed. The string network collapses completely the moment you reach the QCD phase transition, because then you start tilting your potential. The symmetry is gone, and they are able to roll down to the global minimum. Now, in the image that I showed you earlier over here, which is just the axion field, you can already see these axion strings. So the 2 panels over here are a zoomed in region around the spot over here. And you can clearly see the axion string stick out by basically forming a pole in this 2D slice through a 3-dimensional field. So that is an axion string over here. Now, if you look at the other component, your radial mode, which is shown in the spot down here, you can see that the axion string typically has a characteristic width, which is given essentially by the radial mode mass. And this this width of the string is actually what makes numerical simulations really hard. So how are those simulations typically done? Now, axion strings, the way you simulate them is actually pretty forward. Essentially, what you just want to do is you want to write down your equations of motions for your complex scalar field, and you want to solve that on a large 3-dimensional lattice, where you just solve on each grid side, you solve these equations of motions. The reason that is hard is because, as it turns out, you have 2 different competing scales in your problem. On the one hand, you have the string width that I just showed you. And the string width is actually getting, if you simulate in co-moving coordinates, is actually getting smaller and smaller over time, because the radial mode becomes heavier and heavier. And that just becomes a problem because you want to resolve those string cores. So you need a relatively large lattice or a relatively fine lattice with a lot of grid sides in order to resolve them. And then the other scale is given by Hubble, because the typical size of one of those axion strings is given by Hubble. So if you want to simulate these axion strings, you need to have at least 1 or 2 Hubble volumes in your simulation in order to have enough statistics and not run into finite volume effects. So you have these 2 competing effects that you have to have a really large volume, but on the other hand, also really fine resolution on those axion cores. And that problem just becomes worse and worse over time, because in co-moving coordinates, a Hubble volume becomes larger, whereas the string cores become smaller. Now, that is a problem that you can also see if I just go back to the plot that I showed before. But now I'm going to animate it, and you can see down here how the string core, as I've said, the string width just becomes smaller and smaller over time, while the size of a Hubble patch is indicated here by this yellow box, which, as I've said, in coordinates is just getting larger and larger. So, resolving string cores while simultaneously also keeping a large enough volume is really what makes these simulations so hard computationally. Now, in the following, I will quite often show plots that will include this quantity log mr over h. Basically, what this log mr over h is just a quantification of the scale separations of those 2 competing scales. So the larger this value, the larger the scale separation is, where mr is just a measure of the string width, and h is a measure for the Hubble size. Now, as I've said earlier, we ideally want to simulate the entire time between the Pq phase transition and the QCD phase transition. Now, the QCD phase transition, at that time, the scale separation log mr over h is around 70, which is way too large to simulate on any kind of grid. You have basically 70 orders of magnitude in between those 2 different effects. There's just no way to simulate that at all. So basically what you have to do and what you're stuck with is you can only simulate some time after the PQ phase transition until you run out of resolution and out of volume. And then you will rely on extrapolations to go all the way to the QCD phase transition. Now, that is just unavoidable. You will always have to do these extrapolations, but in order to improve your extrapolations, you basically want to simulate out as far to as high logs as you can. That is basically your ultimate goal, because that just adds extra data points to extrapolation, and everything becomes more clear. Now, everything I've told you so far is actually not new. Like, people have been doing these kind of simulations since the 1980s. Of course, very early on like very small grids, because of computational resources were rather limited back then. Now, we are also running the same kind of simulation. However, we bring an extra twist to it, and that is called adaptive mesh refinement. Because ultimately, if you look at images like this, it becomes really obvious that there's not really much going on except at those Axion strings. Only at these Axion strings, you actually need a high resolution. And the rest of the field, those are relatively smooth. There's not really much going on. Now, what adaptive mesh refinement allows you to do is you can have a much finer grid in certain spaces where you need it, basically around the Axion strings, but then have a very coarse grid and save a lot of computation time in regions of your volume that you're not really interested in that much, and where you don't need such a high resolution. Now, that's a relatively obvious approach. We are the first one to actually implement it and practice. Now, this is just an image how it looks like in 3D. So we have really like a fine grid around the string cores, and then we reduce the resolution of the grid the further away we go from those Axion strings. By using that technique, we were actually able to, we're not only able to maintain a higher string resolution, but ultimately we were able to have about 3 orders of magnitude leap in dynamic range of a previous simulation. So we were, able to push these limits quite a bit forward. Now, to show you how that works in practice, so this is a function of time essentially. So over time, the scale separation, of course, increases. What is shown on the y-axis is the string width. Now, the string width, of course, is dropping over time because the string width is getting smaller and smaller. What adaptive mesh refinement basically means is that we just add another finer grid around the string cores at a time where we hit a certain threshold, and then we basically bump it up, the string resolution, by a factor of 8. And then we just keep on doing that every single time we hit this threshold. We just add another even finer grid around the string cores. Whereas just doing it on a static lattice, you can't do that, and your string resolution will drop all the way down to until a point where you just have to stop your simulation. Whereas this, in principle, could go on forever. Now, I'm already referring here to previous works, in this case by Marco Gaggiotto, Ed Hardy, and Giovanni Villadoro, which I think at least some of them are also in the audience. Now, the reason I want to point out this paper and specifically is because there's one of the standard references. They ran the previously bit larger simulations on that front. And I will also refer to those 3 people throughout the talk probably a couple of times to compare to their results. So whenever I mention their names, this is the work I'm referring to. Now, let's jump straight to the results that I have. So what I'm going to do now is just show you a couple of animations first of like how our simulation actually looks like. What you can see here is the Axion energy density. It's a 2D projection of the 3D Axion field. And what you can see here is you can clearly see how those Axion strings, as they evolve, they stand out as regions where you have a really high Axion density. So those are these Axion strings. They stand out with, as having a large energy density in axions. But then on top of that, you can also see how, especially in places where these Axion strings have a very large curvature, you can also see how they send out literally shock waves of axions. And those have to be treated and resolved properly too. So we actually also have extra refinement levels and extra resolution around these points in order to resolve these shock waves properly. Now, of course, our simulation is ultimately in 3D, so this is basically the same kind of animation, but now rendered in 3D, where you can see all the Axion strings roaming around, overlaid with the Axion energy density in halos. And now you can actually see how these spherical shock waves are traveling outwards and dissipate over time. Now, the simulation was rather large. We used about 70,000 CPU cores for about 3+ days. But yeah, ultimately, we were able to get a 3 order of magnitude improvement in dynamic range. All right, so now what do we actually want to get out of this simulation? So our goal is, of course, to determine the Axion mass. In order to determine the Axion mass, what we need to calculate is the Axion number density, because that's what sets the relic density ultimately which is what we want to compare with. Now, in order to get the Axion number density, we need two different quantities. First one is we need to know the total string length in our simulation, because the more strength you have, of course, the more axions we will produce. So that is relatively easy to just measure in your simulation. You just need to figure out where your strings are, and you need to, just sum up their length. On top of that, you also need to understand the evolution of this length, because as I've said, you ultimately rely on extrapolations all the way out to the QCD phase transition. So you also need to know how they evolve over time, this kind of string length. Now, the second quantity is the Axion spectrum. So with that, basically, I mean just as how much axions does a typical string segment actually produce over time. So that's the second quantity that you're interested in. That's a little bit harder to get from your simulation, but ultimately you do it by Fourier transforming the power spectrum and computing the power spectrum of the field while masking the strings itself. All right, so let me show you some of the results. So the first thing is the string length, what is shown here again, just as a function of time, or as a function of the scale separation. On the y-axis, you have the string length per Hubble volume. And what we find is that it is logarithmically increasing over time. And that is entirely consistent with the previous work by Marco and Giovanni and Ed. So there's nothing really new in what we find here. It's completely consistent with the kind of stuff that they found already. So fitting function to it, we can extrapolate this value, and all the way to log of 70, we expect this quantity to be somewhere between 13 and 17. Now, the other quantity, and that is arguably the more important one, is the Axion spectrum. So the way you do it, as I've said, is you basically compute the power spectrum of your field. That, as it turns out, can be relatively easily described as just a simple power law with a power law index of Q. And it's that parameter that is really of interest here, because it defines whether your spectrum is UV or IR dominated. The reason that's important is because if you have, mostly UV emissions, so Q smaller than 1, it basically means that you only produce very few axions. They all have a relatively high energy, but you only have very few, so your axion strings would contribute only very little to the overall number density. In the other case, if you're IR dominated, it's the Q larger one, it's the opposite. You produce lots and lots of axions. They all have little energy, but your number density is going to be very, very large, in which case axion strings produce, are dominating the overall number density very, very quickly. So what do we find? What we find after following basically the same procedure as Marco and Ed and Giovanni, we find a index of Q that is relatively scale invariant and around 1. So it is somewhere in between UV and IR dominated. And most importantly, it doesn't actually seem to evolve at all, and seems to stay around Q equals 1 throughout all the time. Now, the what I want to point out here is that this actually seems to be somewhat inconsistent with what Marco found. They found that their spectrum was initially UV dominated, but then if you extrapolate it, it becomes IR dominated at some point. So their number density was very quickly swarmed by Axion strings. Now, we seem to be inconsistent with that. However, you also only marginally rule it out. So at the end of the day, I think it all just means that there's more work to be done. However, I want to say that we do have a larger dynamic range. So yeah, basically it's just there's a lot of systematics that could contribute to that. And ultimately, we need to study those systematics more importantly, more carefully. Now, how is the Dogmata relic abundance actually calculated at the end? So we already have this number I showed in the previous slide. That's something between 13 and 17. Now, this is something you need to get from the Axion Spectrum. It's basically just the inverse Axion wavelength at the string rate at the time of the QCD phase transition. The way you calculate that kind of quantity is by effectively integrating the power spectrum over here. You numerically integrate it in the IR region, and then you do a power law fit in the UV region over here. And there's some cutoffs involved over here. So what you do is you also compute that quantity then at different times, and then you can fit it, which gives you the parameter delta. And ultimately, that's what enters your calculation of the Axion density from strings. So this is really the formula. You have that determined from the Axion spectrum. You have the log of 70 at the QCD phase transition. You determine that from your Axion string length. If you plug in the numbers, we find the value that is somewhere between 14 and 180 micro eV. And that does contain extra subleading contributions from, for example, the string network decay, something that we had simulated a couple of years ago. Now, to put that on a little bit more context, and on the normal exclusion plot, 40 to 180 micro eV is somewhere over here, which is unfortunately slightly too heavy for ADMX and Haystack, though they might be able to reach the lower range, but it's definitely difficult. Now, to put that even more into context with previous work, so we had a paper a couple of years ago, and Vincent Clare and Moore also ran some stuff where we found that the Axion mass is somewhere around 25 micro eV, which is somewhat lower. However, that work had the assumption that the string radiation is subdominant, which turned out to be not entirely true, which is the main reason why this value is somewhat on the low side. Then the work from Marco, Ed, and Giovanni, because they had this logarithmically increasing power law index, they find a much larger mass than we, around 500 micro eV, more than 500 micro eV. However, that they correctly identified that string radiation dominates the overall number density. And our work is somewhere in between. So I see that as a case of we are slowly converging to a more precise result and narrowing down the range and reducing systematic uncertainties, which I think brings me also to the next slide already. So we did, especially because we showed such a different power law index of in Q than previous works, we did a whole bunch of different systematic tests, mostly because when fitting this power law index, you have an IR cutoff, which is just given by the Hubble size. You also have a UV cutoff, which is given by your string length. So ultimately, you can only fit a region in between. Now, where you exactly place these cutoffs is somewhat arbitrary. So in this case, we tried different UV cutoffs, and you can see that if you actually push it closer and closer to the scale where you're breaking down, you actually start seeing some increasing slope as well. So that is definitely, if the more we try to be as conservative as possible, and that is ultimately what gave us the constant slope. But given that this is an arbitrarily chosen parameter, there's definitely more tests that needs to be done on that front as well. Similarly, also on the other end, there's also a cutoff on the on the UV cutoff. And also here you can see the closer you push it to the limit, the stronger, the larger your index in Q actually becomes. So we chose a parameter over here that seemed to have been somewhat converged already, but again, more work is needed to properly quantify all these different parameters. Another systematic uncertainty is your resolution on the Axion strings. So the simulation by Marco and company, they at the very end of their simulation, they resolve string cost by one grid site, whereas we try to resolve them by at least 4 grid sites throughout our simulation. But we also ran some tests where we reduced the grid site by just, also to 1. In that case, again, it seemed to have produced a somewhat larger index for Q. So again, also the resolution on the string course seems to really affect these results. So that is another systematic uncertainty that needs to be studied very carefully. And then, of course, we did more systematic tests also on the adaptive mesh refinements framework, because we are the first one to use it. So we wanted to verify that it actually works properly and that there's no difference between a static grid and an AMR grid, which seems to be the case throughout a large time frame at least. Now, there are a couple caveats to the general analysis, and that's a slide that Ben, I think, made. So, of course, it is always possible that we made some kind of mistake. However, we are also running larger simulations now with more systematic tests, and I think more than is on the next slide. Then the general assumption, the Pq symmetry has to be broken after inflation. Hold on. Well, okay, Jesus. That should be probably after inflation. So the general assumption is that the Pq symmetry should be broken after inflation. If you break it before inflation, you have an extra parameter and you can't really determine an Axion mass. Now, third caveat is, of course, if you have some other non-standard cosmology like early meta domination, then also in that case, our assumption and our result won't hold true, because then the extra modifications to the evolution that we are not simulating. And then the fourth assumption is that we have a domain wall number of 1, because if the domain wall number would be greater than 1, then all the dynamics after the QCD phase transition would be very different. Most dominantly, you would have stable domain walls and most likely long-lived Axion strings. So in that case, also, the result would be different. Now, in order to address all the systematic uncertainties that I already talked about and to refine results a little bit more, we are currently running even larger simulations. Part of them are also running not only on CPU clusters, but we're also switching to some GPU accelerated calculations on the brand new Permuta cluster that is sitting in Berkeley with apparently a really nice view over the Bay Area. And with that, I'm going to the summary. So I told you how it is possible to predict the Axion mass with the caveats that I just mentioned 2 slides ago. Most importantly, the Pq symmetry has to be broken after inflation. In order to make such a prediction, you need to study the Axion string network really carefully. The reason you have to do that is because these Axion strings are ultimately what sets the Axion number density, as they're the main producer of Axions. In order to push the limits of these numerical simulations, we introduced the adaptive mesh refinement to the problem. And with that, we were able to achieve a roughly 3 order of magnitude improvement in dynamic range. And in terms of what we are finding is there are 2 important quantities with the string length and the Axion spectrum. The string length we find logarithmically increasing, for which we have some theoretical understanding. It's also consistent with previous results. But we also find a scale invariant Axion spectrum, which is something that is slightly inconsistent, marginally inconsistent with previous results, but more work is needed. And in terms of Axion mass, our prediction is somewhere between 40 to 180 microeV. So yeah, thank you very much. Are there any questions?
Okay, thanks Malte a lot for the talk. And now it's time for question. So whoever wants can just raise the hand, and I will give the word. Let's see. So Joachim, you can go ahead.
Hey Malte, thanks for the wonderful talk. So the discrepancies between your result and Gorbenko's, is there? Can you say a bit more about what you suspect are the reasons why they see this increase with log m over h and you don't see it?
Right. So there's a whole bunch of things that it could be. My suspicion is that, so whenever you set up these simulations, you can choose different parameters, and they are always like a trade-off between systematic and statistical uncertainty. And we kind of went different routes there. So we try to minimize the statistical uncertainty, the systematic uncertainty as much as possible, because that is the one that is really hard to quantify. So we were more conservative. We solved them by, like, one grid site at the end of their simulation is represented by 64 grid sites in ours. So we try to really push the resolution there, and that might have some effect given the tests that I showed on one of the slides. Similarly, we were a bit more conservative on the UV and IR cutoff that we chose when doing the fittings of the power spectrum. And again, like that could contribute to the same to that as well. We sacrifice statistics, so our error bars, if you compare our two plots, were like drastically different. Ours were much larger, even though we had a larger simulation. So those are things that could contribute to it.
I see.
But we need to do more tests in order to actually verify that.
Yeah. Do you have any strategy for pushing this even further, covering even more orders of magnitude to maybe see the behavior over even longer time scales?
I mean, it is what we're doing right now in a sense. It's basically just throw more CPU time at it. There's also just generally optimizations in the code that you can do. But in terms of actually new strategies, it's gonna be hard. I don't think there's anything obvious at the moment. So yeah.
Okay. I'm anyway curious to see the next iteration of this.
Oh,
Thanks
me too.
Thanks a lot.
Thanks.
Any further question? Okay, I don't see any. I actually have one, like, it's more accurate. I think that I discussed this with,
one.
Yeah, I have a quick one. Like, I think that I discussed it a bit with Matt Rees, but I want and Ben at some point. But I wanted also to have your opinion, or anyone else in the audience, of course. So you focus a lot for the final abundance and mass on this one of the two log, right? This C, right? But you have another log. You have another log in principle. It's just the tension of the string. Okay. Now, I mean, what I mean is that, is there any kind of UV completion or dependent that you can expect from model building that could actually also alter the final abundance from that other Xi, or the evolution in time, or it will be always kind of a marginal effect? Even just the difference between, the Web and the mass of the scalar, if you think about breaking.
Oh, that's an interesting question. I mean, I would assume so, that there's something you can do in order to alter that, but I don't actually fully know. Now, one thing I can say, since you mentioned the string tension and the log that appears in there, that one is probably directly related to the log that you can see in the string length. But yeah, I mean, yeah, probably there's something you can do in order to alter it.
Okay, Josh wanted to add something probably at some point. He unmuted himself. I don't know if it was a mistake or not.
I actually have a question since 10 minutes ago.
Okay. If Josh doesn't want to add anything about my question, then you can ask your question. Thanks, Malte, by the way. Eduardo, you can go ahead.
Yes, no, I was wondering, like, specifically talking about this logarithmic dependence of both Xi and the string tension. Can you briefly comment on on how sure we are from a theoretical point of view that actually there is no double counting in the abundance of actions that you produce from strings compared to the actions that you expect from misalignment mechanism. Because there was some claim last year that actually the description of the string of string action is actually artificially enhancing the Axion dark matter abundance by string decay, and that actually the Axion abundance is set by the initial misalignment angle anyway.
I'm gonna be honest, I have to refresh my memory regarding that work. It's been a while since I looked at that.
There were two papers by Michael Dine and collaborators.
Right. If I remember correctly, they were supporting also scale invariant. Maybe Josh, you can correct me, but if I remember they were correctly, they also predict a scale invariant spectrum, so one that isn't logarithmically increasing, pretty much exactly what we found. So I think their results were consistent with our results. However, as I've said, I need to look at their papers again. I can't fully remember.
Well, but even if you look, even not looking at, it's not my, probably the paper that you remember was not by Michael Dine. There was another paper more recently that basically was just saying, yeah, in principle, this could be one or the other, and we need more data, but was nothing really.
Right.
It was like, I don't remember, it was like, if it was Gregory Moore, or I don't remember, probably Josh or Giovanni in the audience remember better, but I don't think that there are like indication, actually, probably should be the opposite, that theoretically should not be.
Yeah, so I think the paper you might be thinking of is, there was a paper by some authors whose names I can't remember now, where basically they took results from a few different simulations and took the error bars on those simulations and said, okay, like these are the central values, and now these error bars are the standard deviation for some Gaussian prior, and just like marginalized over the different simulations that they had in their sample. I'm not sure how much that makes sense. Like, these simulations all have like pretty different assumptions going into them. Like the ones we did a long time ago, we're just assuming that string or that string emission was subdominant. And so I'm not sure like what a sensible way of joining that in a Bayesian analysis is with a simulation like this, where we're specifically trying to quantify that string emission. And then I think maybe a separate issue is that there were some papers sort of between 2010 and 2015 that were trying to account for the Axion abundance. And what they did is they had some simulations of the Axion field, and they calculated some energy density associated with the Axion field. And then they also said, okay, strings basically behave in this way, and domain walls basically behave in that way. And they made some analytic arguments for what the energy density associated with those strings and domain walls should be, and just like added that back into the simulation results. And I think that might be the overcounting that you're thinking of, Eduardo. Because of course, like when you do these simulations, you just have the strings and the domain walls in your field. So if you counted up the energy density in the field, you already have some strings and domain walls in the first place. So it's a little bit unclear how to separate things out at that level. I think what we're doing here is we're just looking at when strings are present, and we're not looking at total Axion density. We're looking at like changing Axion energy density in regions away from the strings. So I think we are, along with Marco and Giovanni, are sort of more carefully accounting for what the strings are actually doing in a way that's like pretty isolated from what you would of course want to simulate in detail, which is this misalignment dynamics at the QCD phase transition. Did that clarify? I think I was all over the place.
No, that's okay. Also, because I think that I agree with you also. The other paper that probably Eduardo like Dine, the other was what in the marsh, but that was not
No.
Probably,
Well, I should find
yeah, find the reference. In any case, I think that I don't see other hands raised like
can
in
I
the
just
chat.
one very quick question? Are you planning to tackle also the n larger than 1 case at a certain point, or?
We don't have any immediate plan, but it's certainly something we could do. It's, yeah, I mean, it's something we can definitely think about that. Just not on our
just
immediate
wondering if you
list.
were already doing something, just to understand what was the timeline of the next results.
Yeah, maybe I can point out that, like, if you're doing the n larger than 1 case, like you haven't. I mean, things are even worse, right? Because here we've just been talking about this problem with the hierarchy and scales between Pq phase transition and QCD phase transition.
We have an additional scale in that case.
But now we have a new scale, which is the explicit breaking. Yeah. So you've made this.
But on the other hand, it's also true that probably you don't have the problem of I would expect the contribution from the walls to dominate anyway, because like the Axion population you produce is much less redshifted. So in that case, probably you just have to focus on the very late part of the evolution of the string wall network. But I'm not doing any simulations, so
yeah, but technically that is also difficult to just simulate because they're such extended objects more than strings.
So can I add something for just hello?
Sure, go ahead, Marco.
Just for hello everybody. Thanks for the nice talk. No, I just wanted to say that maybe the reason for our disagreement is possibly related to the initial conditions in the simulations, because we set different initial conditions in this case, and we see that actually the time evolution of the full spectrum, not only of the slope, is different. But in particular, in your case, you have some wiggles in the spectrum, and the idea is that these wiggles are coming from the emission of real modes or heavy axions, very energetic axions from the string cores. So strings essentially oscillate. They oscillate because it exists bound state of the radial mode on the string. They oscillate and they emit heavy modes, heavy radial modes, and heavy axions. And these essentially contaminate the spectrum, especially at small times. And so essentially, those may be the source of kind of pollution of spectrum and disagreement. And maybe one thing to do to kind of solve the problem is to do this fast string system, which is essentially the same system with this quartic coupling decreases in time properly, such that the string core is the same moving coordinates. And this will probably clean up a bit the spectrum. And this is, I think the main source of disagreement, especially. And of course, this disagreement will go away at a large log where this emission from this bound states will disappear. That's the only right. And so I suggest to do these fast string simulations to check this point. They're not super hard.
Actually, just not a comment related from the MIT people. I think that we can stop recording for this session and we can actually anyway continue discussing because the Zoom room is open. But given the discussion was long, I think that now we take like 15 minutes, like formal, let's say, break. We reconvene at 6:45 Central European time or whatever, something 45 for your time zone. And so if the recording can be stopped and we can